Welcome to Lesson 8's checkpoint. So I have my review up so I can use it with the checkpoint, and I'm just modeling again how I would use it to help me answer the questions. So it says use triangles to answer the question. Which statement about triangle ABC and triangle DEF is true? So we have triangle ABC is not congruent to triangle DEF. We have there's not enough information to determine either triangle ABC is congruent to triangle DEF or triangle ABC is not congruent to DEF. Or triangle ABC is congruent to triangle DEF by the side-side-side congruence postulate. Okay, so they're giving us a clue that it's the side-side-side congruence postulate. So I'm going to look at Lesson 8's notes and see what is the side-side-side congruence postulate. And it says if three sides in one triangle are congruent to the corresponding sides in another triangle, then the triangles are congruent. Okay. So what are corresponding sides? That means they're the sides that match up. So vertex A is going to correspond to vertex D. So A and D are corresponding vertex. Vertex B is going to correspond to vertex E. So B and E are the same, are corresponding vertexes. And then vertex C is going to correspond to vertex F. Okay, so now we need to check for corresponding sides. And how can we determine corresponding sides? They're going to be the ones that are in between corresponding vertexes. So A to C, this side length is going to correspond to D and F because that's between the corresponding vertexes. And if we notice, they're both 3.6. So far we have one set of corresponding sides that are congruent. So now let's check another one. A to B's corresponding side is going to be D to E. And this side length is 3 and this side length is blank. So I'm not sure what that is. So let's check one more. F to E is corresponding side from C to B, and this one is 2.2 and this one's left blank. So we only have one corresponding side and then the other information is alternating, so we can't really determine if those sides are congruent or if they're not. So then there's not enough information. It could be that they're congruent or it could be that they're not. We need those corresponding side lengths to know. All right, question 2. Use the triangles in the scenario to answer the question. Ellie states that triangle ABC can be proved congruent to triangle DEF by using the side-side-side congruence postulate. Is she correct? Why? Okay, so side-side-side congruence postulate is corresponding sides are congruent, then the triangles are congruent. So let's set up our corresponding sides. So again, our vertex A is going to be corresponding to vertex D. So A, D. Vertex B is going to correspond to vertex E. So B to E. Vertex C is going to correspond to vertex F. Okay. And then we're going to set up our corresponding sides accordingly. They're going to be between corresponding vertexes. So AB, that side length is going to correspond to DE, and they're both 3.2. So one corresponding pair. Then we're going to check B to C. Corresponding side would be E to F, and if you notice, I'm going from corresponding vertexes to the other corresponding vertex. Those are both 3. 1 second. Hey, honey, I need you to go and watch your movie while I finish this.
Mommy, watch my movie with me. It's over.
It's not over yet. Moana is still playing. I will be another, let me tell you, I'll be another 15 minutes. And then I'll be right out. The more you come in, the longer I'll be. So go outside and wait patiently for Mom. I'm going to hurry. Watch Moana. What is Maui doing?
No, that's the monster.
Mm-hmm.
That was just a fish hook.
Okay. Go sit on the couch and watch Moana, and I'll be right back out. Okay. All right, so the corresponding side for B to C would be between its corresponding vertexes. So B's corresponding vertex is E, C's corresponding vertex is F. So between EF, we have a measure of 3. They're both 3. So then our last corresponding side is from A to C and D to F, and they're both 3.6. So the corresponding sides are all congruent because they're all the same measure. So Ellie is correct because there are 3 pairs of corresponding sides with equal measures. There we go. That's exactly what the side-side-side congruence postulate is. Okay, then we're going to go to question 3. If triangle ABC is reflected and then translated to obtain triangle DEF, what is true about triangle ABC and DEF? How do you know? Select at least 2 answer choices. Select one answer choice for the first question and select at least one answer choice for the second question. Okay, so we're told that the triangle is reflected and then translated. And I'm thinking back, okay, those sound familiar, and I want to see if reflection and translation are anywhere in this notes, and they are. They're from lesson 6. Again, a reflection is a rigid transformation, and it's also an isometry, and translation is a rigid transformation, and it's an isometry, which means that the distance between the new points are the same in length, and it preserves the distance of length and angle measures. So rigid transformations preserves the distance of the length and the angle measures. And in order to have congruent triangles, we have to have the same distance measures and the same angle measures. So let's select at least 2 answer choices. So the first one is a translation is an isometry. That's true. There's not enough information to determine whether triangle ABC is congruent to triangle DEF or triangle ABC is not congruent. No, that's false. We have it. Reflection is not an isometry. It is an isometry. So a reflection is an isometry. Translation is an isometry. And then in order to determine if triangles are congruent or not congruent, each pair of corresponding sides and angles must be shown to be congruent. Or we have triangle ABC is congruent to triangle DEF. Yes, they are congruent. And the reason why they are congruent is because a reflection is an isometry and a translation is an isometry. Okay, question 5. I want to do a proof. So question 5, use the information to complete the proof. Given line segment AC is congruent to line segment AD, line segment AB is a segment bisector of line segment CD. Prove that triangle ABC is congruent to triangle ABD. Okay, so I want to mark out here what they gave me because it helps me visualize it. So they say AC is congruent to AD. So AC is congruent to AD. And remember, tick marks show congruency. And then AB is a segment bisector of CD. And I kind of recall maybe this is what I'm thinking. What is a segment bisector? So if I were to scan through my notes, I'm looking for segment bisector in the left-hand column. And perpendicular bisector, midpoint, segment bisector. Okay, so bisector, a line, ray, or segment that divides a line segment into two congruent segments. Okay, so that means whatever it's dividing has two congruent parts. All right, so AB right here is a segment bisector of CD. So C to D was bisected. That means that from C to B is going to be congruent from B to D. So I'm going to use 2 ticks because AC is congruent to AD, and we do not know if CB is congruent to AC. So we're going to use different tick marks. Okay, now we need to prove that triangle ABC is congruent to triangle ABD. All right, first statement, AC is congruent to AD. Given. Yes, it was right here in our given section. AB is the segment bisector of CD. Given. Yes, it was right there in our given statements. Then it says BC is congruent to BD, and the reason is a blank. So BC is congruent to BD. Why? And the options are definition of segment bisector, definition of congruent segments, B is the midpoint of CD, or segments are split in half by a midpoint. Okay, so then I'm thinking, well, how did we know that BC is congruent to BD? And it came from this statement that was given, that AB is the segment bisector of CD. Segment bisector means that the segment that divides a line segment into two congruent segments. All right, so it's by definition the segment bisector. That is our definition of what a segment bisector is. That's how we concluded that BC was congruent to BD. So then the rest of the proof is filled in. So that was the only one we needed to answer. So then I'm going to see if there's, okay, we're going to jump to question 7. A window is made of 2 panels of glass as shown. Prove that the 2 panels, triangle ABC and triangle ADC, are congruent. Given, AB is a reflection of AD. Okay, given segment AC is a segment bisector of DB. Prove that triangle ABC is congruent to triangle ADC. All right, so AB is a reflection of AD, given. That means the next statement is that the measure of AB is equal to the distance of AD. Well, how do we know that? We know that either is it a definition of a segment bisector? Is it given? Is it a definition of congruent segments? Or is it because a reflection is an isometry? So let's scan again for isometry. Isometry is a function that moves one set of points to a new location where the distance between the new points are the same length. It preserves distance, length, and angle measure. Well, it was given that a reflection, right here, reflection is an isometry. So a reflection is an isometry, and that means that it preserves the distance, length, and angle measures. So that is why we can say that AB is equal to AD. All right, and your help is called Circling the Neck, and the benefits of this are to release tension in your neck, and it allows, thank you, I'll be right out. Sorry for the interruptions. It allows energy to move between your head and your body. Hey, go play. I'm almost finished. Thanks. Again, it's called Circling the Neck. It helps with tension headaches and it releases tension in your neck. And we naturally do this. When we're stressed, we just take our fingers and we rub it behind our neck, and you're just going to rub it all the way down. So the reason why you naturally do this is because it really does help just release your tension. So if you're feeling all pent up, take your fingers and just circle around down along your neck while you breathe. Breathing is key. It helps move your oxygen, increase the oxygen in your bloodstream. So take nice deep breaths. All right, and that again is called Circling the Neck.